In our previous lessons, we were working on solving systems of linear equations graphically, by hand and using technology, whether it was the graphing calculator or Desmos. Today we're going to focus on solving systems of linear equations using algebraic means. And the first way that we're going to look on that is using our concept of substitution. So remember, a system of equations means you have two or more equations with your variables. And our first equation here is y equals 7. And our second equation is 3x plus 5y equals 44. So when we're talking about using substitution, we have an equation where the variable is solved for. For us, we have the y equals. And we can take what y is equal to and substitute it into the second equation. So if we know that y is 7, that means in our second equation, 3x plus 5y equals 44, we could put 7 in place of y. That means 3x plus 5 times 7 is 35 equals 44. Now it's just one equation and one variable to solve. And we know that to undo this equation and solve for x, we would subtract 35 from each side, which gives us 3x equals 9. We're getting closer to getting x alone, so what we have to do now is undo the multiplication of 3 by dividing each side by 3. And we know that x equals 3. So we know the value of x. We also know the value of y. So we know the solution to our system of linear equations would be the coordinate 3, 7. And algebraically, we could check it by substituting the y value into each equation and the x value in each equation to make sure it's balanced. Well, y equals 7, 7 equals 7, we're good there. And if we put 3 and 7 in, 15 and 35, 9 and 35 give you your 44. So again, because there's no context to this equations given, we write the solution as a coordinate. So algebraically, we found where those lines intersected, and we didn't have to put them into slope-intercept form and graph them by hand. We have an algebraic means to do that. So let's look at another example. Here we have y equals 3x plus 2 and x plus 2y equals 11. So thinking about your steps, do you have an equation where a variable is already solved for? Do you have an x equals or a y equals? Our first equation, we have a y equals. So if we know what y is equal to, we can take that and substitute it into the other equation for y. So we're going to take 3x plus 2 and put it in place of y in the second equation. So 2 times what y was representing would give us 6x plus 4. Notice now you have one equation with one type of variable to solve for, x. So what can we do? At this point, we have some like terms we can combine. X and 6x is 7x, so 7x plus 4 is equal to 11. Now we can undo the addition of 4 by subtracting 4 on each side, and then undo the multiplication of 7 by dividing by 7 on each side. So x equals 1. Now remember, we're not done. We need the value of both variables, x and y. So if x is 1, that means I could take it and substitute it back into an equation and solve for the value of y. Well, since we had an equation that started y equals, and that's what we need, let's take the value of x and substitute it into that equation. So 3 times the value of x, so 3 times 1 is 3, 3 plus 2 is 5. So we know that y has to be 5. What's our solution? X is 1, y is 5, so we would write it as a coordinate 1, 5. And again, to verify that we did things correctly, we can take our value for x, 1, and our value for y, 5, and put them into each equation and make sure it's balanced. If we check this one here, it's saying 5 should come from 3 times 1 plus 2, and that's good. If we looked at this one here, we had our value of 1 plus 2 times 5, which is 10. 1 and 10 gives you back the 11. So we know we solved for each value correctly. Let's try this example. So again, we want to solve the system by using substitution. And always look to see, do you have a variable already solved for? Do you have an x equals or a y equals? Well, in our second equation, we have an x equals. We know what x is equal to, so we could take what x is equal to and put it in place of x into the first equation. So we're going to take 2 times our quantity of negative y minus 2. And now notice how we're just working with y's. Let's simplify this. So 2 times negative y, that would be negative 2, and 2 times negative 2 would be a negative 4. And if you notice on the left-hand side of our equation, we have some like terms that we can combine. We've got a negative 2y and a positive 2y, which means we have no y's left over. So it says negative 4 equals 10. Well, we know that those two are not equivalent to each other, and that's a false statement. And algebraically, when we solve and get false statements like this, what does it tell us? It tells us that we have no solution. So algebraically, no matter what value we put in for x and y, these two would never be the same. Now, no solution graphically, do you remember what that looks like? That looks like two parallel lines, right? They have the same slope, the same rate of change, but different y-intercepts. Let's try another. Here you have our system. 11x minus 7y equals negative 14, and x equals 2y minus 4. Again, if we're trying to solve by substitution, ask yourself, do you already have an equation where a variable is solved for? Do you have an x equals? Do you have a y equals? Our second equation has an x equals. So if we know what x is equivalent to, we can substitute it into the other equation. So let's take what x is equivalent to and put it into the first equation. Now we're just going to use order of operations to simplify. So we're going to distribute 11 to both 2y and negative 4. That would give us 22y minus 44 minus 7y equals negative 14. We have some simplifying to do on the left-hand side by combining the y's. So a positive 22 and a negative 7y gives us 15y. Now we can start working on isolating y. So how do we do that? We're going to add 44 to each side of our equation, then divide by 15. So y equals 2. Now remember, we're not done. We need to know the value for both variables. We know y, but we're missing x. We had an equation that x was equal to something, so let's take our value for y and substitute it in there and solve for x. So 2 times the value of y, which was 2, minus 4. Well, 2 times 2 is 4, and 4 minus 4 is 0. So this tells us that our x value is 0, and our y value is 2. So what's the solution? The solution adds to the coordinate 0, 2. Well, if you're noticing here, when it's got an input of 0, it's reminding you this is a y-intercept, so both of these lines would share the same y-intercept graphically. But notice, when solving by substitution, we don't have to look at the graphs to see when they're equivalent, right? We can just use our algebraic means to find where they are intersecting on the coordinate plane. It's okay that variables equal 0. What we want to see happen for a no solution scenario is there's a false statement in your solving. And right now, that's not happening. Let's try another one. Here we want to solve this system of equations. Again, step 1 was asking yourself, do you have an equation with a variable already solved for? Do you have an x equals or do you have a y equals? Well, looking at these two equations, neither one has a variable solved for. However, if you look at the first equation, we could make a y equals fairly easily. To undo the first equation to get y alone, what would you have to do? You would have to add 2x to each side. So let's transform the first equation into y equals our negative 4 plus 2x. Now that we know what y is equal to, we can go through the same process that we have done previously. Let's take the value for y from the first equation and substitute it into the second equation. This way, we only have to solve for x. So let's distribute through 3 to each pair of our terms in the parentheses there. So we've got negative 6x minus 12 plus 6x equals negative 12. Notice on the left-hand side, you have some like terms we need to combine. Negative 6x and negative 6x, well, that's 0. So what are we left with? Negative 12 is equal to negative 12. Well, that's a true statement. Because it's true, what does it tell us? That tells us that we have infinitely many solutions to our system of equations. Graphically, what does that mean? That means that these two equations both represent the same line on the coordinate plane. Therefore, every single point that they contain would be the same, and therefore the two lines would be touching each other. So again, true statement, infinitely many solutions. Just like we were working with graphically, we know when solving systems of equations, we could have one solution where the lines intersect, infinitely many solutions if it's the same line, or no solutions if the lines do not intersect because they're parallel. They have the same slope. So today you're going to do more practice with solving systems of equations using substitution. And then you can confirm that you have the correct solution by doing what we did previously. Taking the coordinates that you have for x and y, substituting them into both equations to make sure they give you true statements.